In memory, there are many processes, and they maintain a virtual address on their own. So what if processes need to transfer data between each other? In the last video, we talked about shared variables, mutual exclusive access between processes. In this video, let's talk about more complicated synchronization issues. Between the two processes, a shared fixed-size buffer is first required. The data generated by process 1 is put into the buffer, called the producer. The other is that the process takes out data from the buffer and is called a consumer. If the buffer is full at this time, then the producer will be blocked and stop production. And if the buffer is empty, the consumer will be blocked and wait. So how do you keep these two processes in sync? This is called the producer-consumer problem, also known as the bounded buffer problem. This question seems simple, but in reality, there will be complicated competition issues. First, we need a variable count, which refers to the number of data items in the current buffer. It is currently empty, so the count is 0. Let's look at the main C language code. The first is the producer. The produce item function produces an item, then determine whether the current count is n, which represents the total number of items in the buffer. Then n is 7 here. Now count is less than 7, so there is no need to sleep. Carry on. Then put the generated item into the buffer. Then increase the count variable by 1 to become 1. In the next sentence, if count is 1, it means that there is data in the buffer. Need to wake up the consumer through a system call, that is process 2. Now we look at the consumer's code. Then it will first determine whether the current count is 0. If yes, sleep. It is now 1. So go directly to the next line of code. Remove item from the buffer. Next, subtract 1 from count to become 0. Next, check whether the count is n minus 1, and if so, wake up the producer. Of course, if count is 0, skip directly. Finally, the fetched data is processed. This looks pretty good. However, if we take the CPU into consideration, generally, the number of CPUs is much smaller than the number of processes. So assuming there is only one CPU, two processes are running alternately. For example, run the consumer first. It runs the first line first, reading the shared variable count. At exactly this time, the CPU switches to the producer process. The producer generates the data item first, then count is not n. Next, insert them. Then count changes from 0 to 1. Finally, count is indeed 1. So try to wake up the consumer. However, the consumers at this time are not asleep. They are awake. Naturally, this signal is ignored. Then the CPU switches to the consumer process. Now that it has been read that the value of count is 0, so start to sleep next. The CPU then switches to the producer process. The producer generated an item, judges the count, and inserted it into the buffer. The count is increased by 1 to become 2. Because count will get bigger and bigger from now on, it will never be 1. Therefore, consumers will never be awakened. So next, keep looping until the producer fills up the buffer and sleeps. Now, no one is going to wake them up. In this way, the two processes will wait forever. Now introduce a solution called semaphore. It is an integer variable equivalent to a natural number. It corresponds to two operations, down and up. It is a generalization of the previous wake and sleep. Wake and sleep just now are from one process to another, and omissions just now appear. The down and up here are the operations of the process on the shared semaphore. Specifically, for example, if there is a shared variable, only mutually exclusive access can be made between processes. In addition, there is a corresponding semaphore. The semaphore is 1 at the beginning, that is, only one process is allowed to read and write at the same time. If there is a process 1 that wants to access, it performs a down operation. This operation will be decrement the semaphore by 1, and the semaphore will also become 0. Then process 2 also wants to access, so it executes the down operation. At this time, the semaphore is already 0. The system will put the process to sleep, and the down operation will also be suspended. Then process 3 wants to access, executes the down operation, and is also put to sleep. At this time, process 1 finishes reading and writing, executes the up operation, and adds 1 to the semaphore to become 1. The shared variable can be accessed. Therefore, the system randomly selected a sleeping process, such as process 3, wake it up. The down operation of process 3 continues to reduce semaphore by 1 to 0, can read and write. Wait until the process 3 ends. The up operation. The semaphore becomes 1, then the system wakes up process 2. Process 2 continues down operation, reading and writing variables. At the end, the up operation. The semaphore is restored to 1. Now we use semaphores to solve the producer-consumer problem. We need a total of 3 semaphores. They are empty, which represents the number of empty buffers, which is 7. 4, which represents the number of full ones, which is 0. Mutex is used to control the mutually exclusive access of processes, which is 1. Then, this is the main code of the producer. This is the main code of the consumer. They are very concise. Suppose now there is only one CPU running in turn. Execute the produce process first. The producer pursues the data item first, and then needs to insert the item. Before inserting, first use a down operation on empty. Decrease the number of empty spaces by 1. Next, mutex uses the down operation, which means it's time to read and write the buffer. After inserting, use up to operate the mutex to end the access to the buffer. For the full semaphore, the up operation adds 1. The consumer code just changed the order of full and empty. Just now, we have learned that mutex can guarantee mutually exclusive access to the buffer between processes. Now we mainly look at the role of full and empty semaphores. Suppose now that the producer generates a lot of items, the buffer is filled. At this time, full is 7 and empty is 0. Next, when the producer wants to insert again, the down operation of empty will put itself to sleep and wait. After the consumer takes out an item, it will use the up operation on empty. The semaphore changes from 0 to 1. The system will wake up the producer process and continue working. The same goes for consumers.